Hello, everyone. How's everybody doing? Hope you're doing fine. And as always, I want to remind you that on the, 8th of June, we have a little conference over there in Sweden, Boris, Sweden. And it's going to be the seventh Rational Physics Conference. So I hope to see you there. And there's always some interesting people that show up. We have a good, very good discussion about physics, the rope model, etc. Okay, so if you like physics, you want to drink some beer, well, now you know where you got to be the 8th of June. And remember, over here in Europe, I'm in Europe, it's summer. So if you're from the lower part of the equator, maybe it's a good time to, to fly with the geese. Anyways, today I have a very interesting, very exciting topic. I want to talk about nothing. You might say, Bill, come on, you've talked last couple of weeks about points, zero-dimensional points. Now that was quite boring, right? You talked about 1D lines. Now how exciting is that? And today you're going to talk about nothing. Yeah, uh, I've got two answers to that. The first one is that someone's got to do the dirty job, and that's me, right? Nobody deals with these subjects in general. The other one, probably a little more important, is that you know um, nothing is about 99% of what's wrong with mathematical physics. Mathematical physics deals with nothing, but it hasn't never figured out what nothing is. It is something wrong with the sound? Please let me know. We'll mute the sound. Could you repeat that? Is there something wrong with the sound? Oh, okay. I received a message from Mr. Walker saying, we'll mute the sound. Exactly what he meant by that, I have no idea. I thought maybe you couldn't hear me or something. Okay, let me continue. Okay, yeah, I'll be talking about nothing. Okay, I was saying that aside from the fact that someone's got to do the dirty work, that's going to be little old me. There's a second issue, and that's that 99% of the problems with mathematical physics have to do with this famous word nothing, this important word. And the problem, the underlying problem, is that nothing is always something. It turns out to be something. They have no idea what nothing is. No one has ever used the concept of nothing. Whenever they roll in there, into what they've got to explain or whatever, their nothing ends up turning into something. Okay, I'm going to give a little introduction on nothing today because whether you believe it or not, it's a big, big topic. So I'm going to be covering a couple sessions with the word nothing at least, I think. And before I get into nothing, I want to talk about some comments that an individual made. And I'd like to address those comments because when people write in an organized manner and have some issues that they bring up, and I think they're important to be addressed, I'd like to address them. I don't like to just brush them aside and say, look, I never saw that, never heard it. And it has to do with, we were talking about points, lines, you could include within that planes and solids. And he decided to define these terms after listening to me. Okay. Now, his definitions are very different than mine. And again, You choose the definitions you want to choose. I just want to clarify in a way, rehash what's wrong with those definitions, the ones he's proposing from my point of view, and why we need to define these words more accurately, okay? Why they're important, especially because they underlie mathematical physics, geometry specifically, right? So we need to know what a point is, we need to know what a line is in order to follow the presenter's presentation, that's one. The other one is we need to establish the foundations of geometry. So you need to define these words if definition is what is appropriate in this case. And that's one of the issues, that's involved here. Okay, let me go with the first one. This gentleman, he wrote the following. He says, point. He defines point. He says the relative center of an object. The word center also varies upon precise definition. This could be the volumetric center, center of mass, etc., whichever definition of center is chosen. And he continues, the point still suffices to represent that center. Okay, what's my criticism about against that? Again, he's equating point with center, right? Could be a geographic center, could be the center of mass, volume, area, whatever. And the red ones are my criticisms at the bottom. I'm saying the center is not a geometric figure, okay? The word center does not represent a geometric figure. That's my first objection to using the word center. And second, we don't define figures in science. We point to them, okay? If you want to use the concept known as center, call it a center. It's very simple. Don't call it point and mean center, okay? That was essentially what my presentations in the past were about. In geometry, which deals with shapes and sizes, right? All figures must be either 2D or 3D. And center is neither one of those, right? So no, the point does not suffice to represent that center as this gentleman suggests. Okay, so that's my criticism against his use of the word center as a synonym of point. For example, we do not use a heart to represent love in physics, okay? And statements such as love moves mountains, that's not a statement of physics, that's poetry. That's a figure of speech, that's fine, that's in ordinary speech. We can't use that in physics because physics is literal and physics is done with objects. The way you do physics really is you illustrate, okay? It's a theory of physics is a movie, essentially. Math is not the language of physics, okay? So therefore, if you're talking about the center of mass or of a volume or of an area or whatever, you're not talking the language of physics. The word center in that case does not represent physics. And center in those contexts, in a mathematical context, usually is an ordered paired or triplet or quadruplet or whatever. So they're talking about locating a point within some certain reference points, okay? So you have all these, what do you call them, frames of reference, and you establish a location. You call that the center. And so center really translates in mathematical language into ordered pairs, ordered quadruplets, etc. And again, the language of physics is illustration. Okay, so I hope that clarifies some points there. For example, one thing I'd like to add to that is that, let me get it here, is that, we don't use words such as, like I was saying that you can't use the word heart to represent love. Not in physics. That's okay in ordinary speech, not in physics. And likewise, you don't use a dot to represent the notion of location if that's what you mean by, by dot, by point, right? Okay, and here I have some examples. Here you have center and location. Are we going to say that a dot represents center, a dot represents location? What do you mean by that? Are you saying that you're replacing love with heart, you're replacing a concept with an object? Same with math, for the distance and length. In math, that's different than in physics. In math, we talk about length and distance, and we measure. So for the mathematician, the word length is equal to the word distance. There's no difference for them because they're talking about meters. They're talking about inches. They're talking about 5 inches, 10 meters, whatever unit number in unit they measured. That's not what it is in physics. In physics, distance is simply the separation between two objects, and length is the continuous um, extent of an object. You treat it as if it were made of a single piece. But we don't care what the length is. You take a pygmy, for example, he doesn't know whether his arrow is 1 meter or a meter and a half. All he knows is one arrow is longer than the other one. That's length to him. And he knows whether he can fit into a cave, because he has this intuitive notion that he's wider or longer or whatever than the cave hole is. That kind of thing. That's physics. Measurement, numbers, that's mathematics. And we don't use the word compass to replace as a synonym of angle. We don't say, this is a compass. No, we say it's an angle. And angle is a concept, compass is a physical object. So we don't replace words such as angle, concepts such as angle with objects, not in physics. Okay. So I just want to clarify some of these things, why those are unacceptable. And you get into situations where like you get Mr. Stephen Hawking, and he goes in there and he uses the point, and he says an event is a point. Event is a point in space-time. What do you mean an event is a point? I thought event was a movie. I thought event meant something happening. And in fact, he does say something similar to that, but you got to be careful with what he's talking about. He says an event is something that takes place, okay? That's something in motion, right? Takes place at a single point in space. That's impossible. Nothing can take place at a single point in space. At a specified point in time, again, time involves at least two frames of the universal movie, so you can't have a specified point. There's no such thing as a moment. There's no such thing as a point in time. Time always involves motion, the word time. So to say, look, this happened at a point in time, at a moment, at an instance, no such thing in science. Okay, that's religion. And he says sending out a pulse of light. Well, sending out hopefully takes more than more than one frame in a universal movie. Two events took place. Again, he says that, right? At different times occurred in the same position in space. For example, suppose our ping pong ball. I just took this as a piece from. That's why it doesn't make complete sense, but it doesn't matter. Suppose our ping pong ball on the train bounces straight up and down, hitting the table twice on the same spot, 1 second apart. One could not give an event an absolute position in space, the positions of events and the distances between them. Okay, what is he talking about? He's talking about a ball, in this case a ping pong ball, hitting the table. So now we're talking about touch. Okay, he's referring to the moment, the exact moment, the instance that that the ball touches the table. So he says from that event, which he calls, which in this case is touch, right? The two surfaces coming together. A light beam comes out, and we say, okay, now we start worrying about when did it touch? Did it touch at the same time? That sort of thing. Okay, but the question is, touch is a special type of verb because touch is a verb. You need two surfaces to touch each other, right? Two things to come in contact to conceive the word touch. But touch is that specific moment in which there is zero distance. And so the question is, touch a verb? Is it a dynamic verb or is it a static concept? And we could go on all over all day long on this word. All I'm saying is he chose a specific example which has to be analyzed very deeply because he said a mouthful there without knowing it. In general, when we talk about events, okay, we are not talking about um, anything that is static. Event is automatically means that you are referring to motion. You're referring to a verb. Jumping is an event, not something that happened at a given point in time, at a given instance, at a given moment. And so we have to be careful, because we're turning verbs into nouns. The word event sounds like a noun. We usually use it as a noun in ordinary speech. But in physics, event is a verb. And so for them to say, look, we can locate this event with 4 coordinates, dimensions they call them on top of that, we can locate this point in space time. We're confusing the language here, and the language here is critical. It is critical. You got to keep all that in mind. Okay, this gentleman also defines what a line is, and so moving up here, he says, line any path that an object takes upon a plane. Therefore, a line can only exist in a plane, and a plane requires 3 objects to define it. Thus, a line actually requires independent objects to give it meaning. If there only exists one path from alpha and omega that passes through beta, then the plane is also a line. Essentially, he's saying that a line is a path, an itinerary along a plane. And again, my objection, the path is not a geometric figure. You cannot say that a line is a path, okay? Not in geometry, not in physics. Maybe in mathematics, maybe in ordinary speech, but not in physics. That's my criticism to that. That's the primary one. But if you want to use the concept known as path, call it a path. Don't call it a line. The word line is always a figure. Never use objects to represent concepts in physics. You don't use heart to represent love. Okay? Physics is literal. Whatever you put on the screen, that's what it is. And that doesn't mean that you cannot do simulations. Okay, like I use the rope of ordinary speech of that you can buy at a store, and I use it to simulate light. But I'm saying that light, that invisible thing that is there that goes or extends really between 2 atoms, I'm saying it looks like a rope. So I'm talking about a physical object. Some people accuse me saying, "Oh, but you're using concepts." No, it's not a concept. Rope, even in the world of the Klingons, is an object. Rope is always an object. Okay, and a line looks like this, like that black line there. If you can't use that thing, then you are not using a line. Okay, so you can see where I'm coming from for some of all these things, all these words, all these definitions. Are footprints a line? You'll hear the relativists talk about geodesics, distance, and they replace that with a line. Well, here you have it. Here you have a line, a series of footprints, okay? And here's the little man just walking around the earth. Is that a line? Is that what you would call a line? Okay. Here you see him walking again, just creating all these footprints or following them. Or is a line a stick? For geometry, we have that thing on the right. That's a line. And, itineraries don't qualify as lines. Okay. So summary that I had the other day for line. These are all the lines that Mr. Whale proposed. And the 2-point line, the between line, the hinge, rotation. He talked about rotation. The row of apples. The single apple that goes from one place to another. His stick, he turns all those apples into a stick. Then he talks about the plowing, what I call the plowing line, or the sliding line, this apple that just slides through the trough, right? And he then throws all that away, and he said, well, we don't need any of that. We're going to do the number line. That's what he does his book with numbers. So the question is, what the hell is he talking about, right? And that's the problem. You need to define exactly these terms, because otherwise the guy can use them in different contexts and he loses you unless he specifies exactly what he's talking about. But again, you start your presentation saying this is a line. You point to it on the board, right? Or you show it on the projector there on the screen. And then you don't use that. And then you just talk about whatever and say, well, the line, is a bunch of footprints or a number line or whatever. Okay, he also defined, this gentleman, he defined what a surface is. Okay, he says a flat surface that can pass through 3 points. Let the two furthest objects be called alpha and omega, let the remaining third object be called beta, etc., etc. Okay. He's saying that it's a flat surface. Okay, the problem here is that surfaces are all 3D. Surface is a term that belongs exclusively to the three-dimensional world. And you say, oh, Jesus, is that true? Yeah, let me show you an example here first. And here it is. Let's see if we can see it. Here's a surface, okay? The outer surface of a 3D object, even if it's an ideal one like a cube, that's what we call a surface, okay? The surface is the whole thing. It's three-dimensional. One side of that is known as a face or a plane. All planes, all planes are the face of a solid. You have to understand that a plane has, belongs to something else. There is no such thing as a standalone plane. If you see a circle, maybe it's the bottom of a cone. If you see a cube, well, who knows what. If you see a square, it's the face of a cube, and so on down the line. Okay, so the word surface belongs exclusively to the 3D world. It belongs to the world of solids. There is no such thing as a 2D surface. The word used there, and that's why we use the word flat, is the word plane, or face, you could call it. But there's no such thing as a flat surface. Not in physics, not in science. In ordinary speech, we say that the surface of the table is flat. That's not applicable to the world of science, because otherwise we're not being precise with the language. Okay, so the only thing in flat, in at least in mathematics or geometry, are the ideal figures. Those are, squares and so on, even the sides of a cube, those you can call flat, but you can't call that side a surface. The surface is the whole thing. We've gotten used to using the word surface in lieu of the word plane or the word face, or, and we talk about flat surface. No such thing. Okay? That's my argument. Okay, you don't have to agree with it. Okay, and then I had here some pictures. Okay, so we have these are 2D planes. You can even have an irregular shape like a 2D blob there. Okay, so not only are they ideal figures, they could be non-ideal figures. Have a blob there, 2D blob. Okay, what else do we have? Oh yeah, one of the things that I wanted to mention, because it happens all the time, is the mathematicians misconceive flatland. Flatland by Mr. Abbott, 19th century, and he talked about all these figures, 2D figures. He wanted to show that there's a difference between the 3D world and the 2D world, especially, that was used a lot by relativists, still being used as an analogy, like saying, well, why can't we see the four-dimensional world of all these four-dimensional beings? Well, he says, because, the same way the two-dimensional flatlander, he can't see you. He doesn't know what up means. And the problem is when they try to look at the world of flatland, they try to illustrate it. They always represent the 3D world of, solids. It's solid land. It's never flat land. And the main point you got to remember is that, they have all these squares and circles and triangles and whatever, and they're moving. Well, if they're moving, obviously they're above the street, right? So if flatland is the street, these guys are floating in air. That's why they can move. So that's a misconception to begin with. But they have a lot more misconceptions. And here I kind of showed the quantum version of flatland. We have Dr. Quantum there. And you can see that first he has to fly through a wormhole to get to flatland. Then he sticks his finger, right through the intersection of a street, but he's got cubes there. He's showing a three-dimensional scene. And again, all the cubes and triangles, all the squares and triangles are moving. So is Mrs. Flatland there. The money in the vault there, it's also 3D. Everything that you see is 3D, even the door opening. So they always misconceive flatland. And you might say, well, Bill, they had to do a cartoon and so on. Okay, fine. But look at always their analysis of the flatland world. It's always 3D, always 3D. I've never seen, there's this book by Timothy Ferris. He writes Coming of Age in the Milky Way. It's a book about mathematical physics. And he shows a flatlander, but it's even worse than this. He shows one of these stick figures, and it's walking on top of a plane. So he's got the surface and the guy standing up on it. It's a totally 3D scenario. And this is the type of error that these people make, conceptual errors, where they cannot visualize the 2D world of flatland. Because if you're going to talk about flatland, it's got to be static. You can't have triangles move around. I mean, you can play around with that, but then again, you're going to run into trouble because people are going to say, "What do you mean the triangle can move? How can it move? Isn't it stuck to flatland? I mean, is it sliding through flatland?" Okay. And again, if it's separated, from the other guys because it's got some kind of height or something. Okay, moving on here. The last thing that this gentleman defined was space. He says a volume bounded by 4 points, la 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 la. Okay, fine. I'm saying space is not. First, we got the problem with the word space. Space is a synonym of nothing. The word space should not be used as a synonym of figure, of object. They say three-dimensional space, two-dimensional space. That is idiotic language. It's idiotic language. Space is not a physical object, should not be used in that context ever. You cannot say two-dimensional space, you cannot say three-dimensional space because space has no dimensions. You got to use object. They're confusing figures with space, with nothing. Okay, subject of today, by the way, if I can get to it. So what is space? Space, that which doesn't have shape. We're done. That's what nothing is. The anonym, something. So if something is that which has shape, nothing is that which doesn't. Very clear, very straightforward. You can use those two definitions consistently. A solid is not a volume. Volume is a dynamic concept. It's a dynamic concept. Volume means, it's the amount of water that the rubber ducky displaces. That's what volume is. It's the push of the water. That's what volume is. So you have to think of volume also from a dynamic point of view. The fact that when you say 3 meters, three cubic meters, what you're saying is you measured here and there 3 times. Okay, so it already involves measurement. So volume is a dynamic quantity, and it's not the same thing to say that a solid or a category of figures known as solids is the same thing as a volume. It's not. Okay, so solids are a category of figures, just like planes. Okay, and a cube is not a volume. Period. I mean, volume is the amount of water that the cube displays. That's what volume is. But cube is not a volume. Cube is a standalone figure. Volume refers to the medium that contains the cube. That's what we call volume. It refers to what the cube does to the ocean, so to speak. Okay. And again, a cube is a geometric figure. In science, we don't define figures. We point to them. Okay, so those are my criticisms. Okay, you can beat me up later. Okay, I'm going to move on to this exciting topic of nothing. And again, we need to define nothing. One because we need to, it's 99% of what's wrong with mathematical physics. They never could figure out what space is, what nothing is. And they've always converted space into something. And it's not only the mathematical physicists. A lot of these fringe guys, they always talk about, or the guys who vouch for the ether, they always say, look, space and ether are the same thing, or space is full of stuff. And we don't know if they're talking about space or space as a container that contains the stuff everywhere. All these things need to be clarified. And by the way, as you probably well know, the relativists also, in mechanics, quantum mechanics, they always treat space as something solid, as made of particles, virtual particles, or having dimensions, 4-dimensional space-time, that sort of thing. So, and they bend it to create gravity. So obviously they treat it as a physical object at all times. So you wonder, is there anything such as nothing in mathematical physics? And that's an important question. That's the kind of question I'm going to be addressing here. And it's not a yes or no type of question. That's something you wake up one day and say, "Oh, I got the answer to this." No, this can be somewhat complicated, you know. And one of the things that they use nothing for, because they do nothing all day long, these mathematicians. And one of the nothings that they do is measure. They measure nothings. They measure lengths and they measure distances. And they measure time. And all those are nothings. You know, all of them are nothing. And you're saying, what do you mean they're measuring the table? No, no, they're not measuring the table. They don't care if it's a table. They don't care if it's a chair or a couch or a lamp. They don't care about that. They need the 1 meter, the number in the unit. Sometimes, you know, sometimes it's just a number. They need to put that in an equation. They can't put table in an equation or the word table in an equation. They can't use that stuff. So they don't deal with physics. They don't deal with physical stuff. They don't deal with that stuff. They deal with the numbers they get out of measurements. That's what they put in an equation. And so that's why, you know, they can only measure things. And that's why nothing, you know, I mean, what are you going to do? Measure nothing, count nothings? 1, 2, 3, 4, 5. I've got 5 nothings. So no, they had to convert everything into something, including nothing. I hope you're not with a headache by now. Okay, so you think I'm the only guy that talks about nothing? Well, think again. I'm not the only numbskull out there dealing with nothing. There's another numbskull, at least one. There's several of them, really. And one of them is a geek, and his name is Larry Krauss. And Larry Krauss, here he is. He wrote a book in 2012, A Universe from Nothing. And you might say, well, is he a geek? Yeah, he's a geek. See, he wears glasses. He does equations all day long. I mean, I'm not insulting the guy. He's really a geek. I mean, he's, I think, the poster boy for geeks, right? Wouldn't you say? And you know, so he goes out there and he talks in this book. And the Wikipedia has a little summary. It says it discusses modern cosmogony and its implications for the debate about the existence of God. So his ultimate goal is to talk about whether God exists or not, specifically whether there was a creator, okay, for the universe, because you have the general relativistic version, or you could say the mathematical physics version, which says that the universe came into existence all by itself, okay? It had no creator. And you have the religious version that says, oh, you know, there was a God and he created everything. And you know, William Lane Craig, he's one of the guys who mostly vouches for that version. He always discusses with people like Krauss, you know, about the existence of God. And the main theme of the book is how we have discovered that all science suggests a universe that could and plausibly did arise from a deeper nothing. Now that's interesting. You say it arose from nothing, involving the absence of space itself. So obviously we have nothing, and apparently nothing is something different than space, because he's talking about, hey, there was nothing and not even space. So space is different than nothing. Keep that in mind, okay? Which may one day return to nothing via processes, blah, 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 blah. Okay. And I have focused on either the creation of something from pre-existing empty space or the creation of empty space from no space at all. So, you know, he clarifies about empty space. You know, he clarifies that term. I don't know if he means by that that space is not the same thing as empty space, right? That's the first one. But then, you know, it's not very clear whether space is a thing. Like, you know, he talks about the creation of empty space. Like saying, you know, that where did that empty space come from? It came from nothing. Like, again, suggesting that, nothing and empty space are two separate issues, okay? Two separate things, concepts, whatever. Okay, and where do we go from here? Well, the first question you have to ask yourself is, what is nothing? What do they mean by nothing? I mean, if he's going to talk about nothing, just like I'm talking about nothing, what do we mean by nothing? I mean, can we follow along if we don't know what the meaning of the word is? So when you look up, you say, okay, usually people identify that with vacuum, with space, with, nothingness, void. We treat them as synonyms. But is that the way mathematical physics treat them? That's the question. And I think the answer is no, and you can see it here. Here you have the first one. Vacuum is space devoid of matter. That's the definition of vacuum that you will find in the Wikipedia. All these come from there, okay? And then you say, okay, is space devoid of matter? Okay, so if we remove all matter, apparently vacuum is space. So now we got to figure out what they mean by space, because I thought vacuum and space were synonyms. So defining vacuum in terms of space and space in terms of the word vacuum, we haven't learned much. So what is space? Well, space is the boundless three-dimensional extent. Blah, 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 blah. Whatever continues after that is meaningless. So they're saying three-dimensional extent. Okay, so I guess at this point we got to find out what they mean by extent. And when you look that up, you find that we have no definition. The first part, you look extent of them, they have all those. They have one for computing and another group for other, none of which have anything to do with instant context. However, they have a little sign there that says you can look it up, extent, in the Wiktionary. Okay, so I looked it up and look at the etymology there, and it says, it comes from the Latin meaning extend. Okay, so a stretch of land or whatever, something that extends. Great. So we still don't know, because they're saying it's the extent. The extent of what? Okay, so extent of land we all understand, but extent alone, what do they mean by that? And the closest you get is down at the bottom, it says noun. Okay, at least they hit that one. Extent is a noun. It says a range of values or locations. That's one notion. The other one is space, area, volume to which something extends. So we're back to space extending. We're going around in circles. We don't have a definition of the word space, and we're stuck because at that point, we don't know what he meant by space. Okay, what the quantum people meant by space. So here, again, space is the boundless three-dimensional extent. We're stopped at the word extent. We have no idea what they mean by extent. Okay, you continue and you keep looking to see if you can find a better definition for vacuum. It says, physicists often discuss ideal test results that would occur in a perfect vacuum. So we have vacuum, we have perfect vacuum now. We have a difference there, right? Vacuum, I thought all vacuums were perfect, but it turns out there's perfect and imperfect vacuums, which they simply call vacuum or free space. Okay, so now we have vacuum is not space, vacuum is free space. I guess free of matter, that would be it, right? Okay, and use the term partial vacuum to refer to an actual imperfect vacuum. Okay, fine. According to modern understanding, even if all matter could be removed from a volume, it would still not be empty. So we got all these contradictions. They say, look, a vacuum is space. Space is vacuum. Okay, we got a circular definition. We got synonyms. Okay, fine. They say vacuum is a space that is free of matter. And now they say, look, even if you remove all matter from space, it still would not be empty. You still would not have perfect vacuum due to vacuum fluctuations, dark energy, transiting gamma rays, blah, blah, all these other junk that is filling space everywhere. And it says in modern particle physics, the vacuum state is considered the ground state of a field. Okay, so what is a vacuum state? Is it one of the states of the union? I guess not. It says, also called the quantum vacuum or vacuum state, is the quantum state with the lowest possible energy. Generally, it contains no physical particles, generally. So that means sometimes it does. And again, we keep going back to a no particle, a no matter vacuum, a no matter space, a space devoid of all matter. There's no such thing in mathematical physics. Because they say even if you remove everything that you can think of from space, there's all these vacuum fluctuations and all this garbage that God put in there, that we can't get rid of. So even though total vacuum is not total vacuum, the perfect vacuum is not perfect vacuum. And just to make things a little more complicated, they say, no, just in case, just in case you didn't understand till now, let's make it more complicated. They introduced virtual particles and particle pairs. They say a virtual particle is a transient fluctuation that exhibits some of the characteristics of an ordinary particle while having its existence limited to the uncertainty principle. Okay, fine. The term is somewhat loose. Yeah, no doubt. Everything is very loose in mathematical physics and vaguely defined. In that it refers to the view that the world is made up of real particles. It is not. Rather, real particles are better understood to be excitations of the underlying quantum fields. And what are those quantum fields? Well, again, it's those vibrations that we can't see that form the vacuum. So the vacuum is never empty. It's always got these fields in it. Virtual particles are also excitations of the underlying fields. Okay, so even those are excitations, right? But these are temporary in the sense that they appear in calculations of interactions. They appear in calculations. In other words, these are mathematical ad hoc artifacts. They can't explain something and say just put a virtual particle and give it all the superpowers you want, because a virtual particle doesn't have to obey any of the rules of classical physics. That's the issue. Okay. Vacuum polarization involves pair production or the decay of the vacuum, the decay of the nothing. They just said vacuum is nothing, but now they're saying no, vacuum is something. It decays and produces what is called a pair production, right? Which is the spontaneous production of particle-antiparticle pairs. So these things were hiding inside the vacuum. They were comprising. They were constituting the vacuum. And they say electron-positron pairs. Now, if I remember correctly, an electron and a positron, at least the electron is part of an atom, and it's considered a particle. So now they're saying that these particles, called electrons, together with they unite with the positive electron, the positron, and these two particles form the nothingness of the vacuum, and they vibrate because they're vibrating fields. So again, we have no idea what nothing is so far. We don't have an idea what vacuum is, what total vacuum is. It never is totally vacuum, totally nothing. According to quantum field theory, the vacuum between interacting particles is not simply empty space. Okay, thank God they clarified that. Rather, it contains short-lived virtual particle-antiparticle pairs. And again, they give some example: leptons, quarks, or gluons. Again, all particles of the standard model. These short-lived pairs are called vacuum bubbles. Right. So we got vacuum bubbles now, like in a tub. According to quantum mechanics, particle pairs are constantly appearing and disappearing as a quantum foam. Okay, so what did you learn in school today, son? At the physics class? Well, not much, Dad. Not much. I learned that the vacuum is something, not that it's nothing. So we got a problem because we don't have a definition of what nothing is, a definition of vacuum, of what space is, all by itself. Okay, we don't have a definition, and that's the starting point. And you can see why Mr. Krauss is going to run into a lot of trouble when he's questioned by ordinary people who are not experts in quantum mechanics or in general relativity or string theory for that matter. And they just ask questions that you might ask. You might say, well, okay, the vacuum. You wrote a book saying the universe from nothing. What do you mean by universe? And that's what Joe Rogan asks Mr. Krauss. He says the following. He says, Let me get the right one here. Yeah. He says the following on Joe Rogan's program. He says, there's always a universe being born. And Joe asks him, where are they? And they're outside the region we can see. Okay, so the fact that we can't see them makes them a different universe. Okay, so he says the edges of our visible universe, space is expanding faster away from us than light. The space between us is expanding, so that galaxy, like a surfer, is carried away from us faster than light. So he changed the word from universe to galaxy, and so Joe kind of is thrown off a little bit and says, "Oh, hold it. Are we talking about a different universe? I mean, just is it just a part of the universe we can't see?" And I guess he was really referring to the galaxy, like saying, there are galaxies we can't see. Are these different universes, or are they part of our universe, and we just can't see them, and we call them what we used to call them, galaxy. And there he clarifies for us, what all these people talk about in mathematical physics. When I was a kid, universe meant everything. But that's a pretty stupid definition. A better definition is an operational one. Oh my God. Universe means that region of space with which at one time we could have communicated, or one time in the future we could communicate with. Because that describes the region of space where cause and effect work. Universe is that region throughout which everything could affect everything else. That's what he calls universe. And in that picture, universes can be restricted in size. And then other regions which could never have affected us and which will never affect us in the future, we call other universes. There are many different versions of the multiverse, but that's the simplest version. Okay, so what is there he talking about? He's saying, we have all these galaxies, really, stuff we can't see, but are within the universe. But he said, well, we're going to call them other universes because we can't see them. We'll never interact with them. We can't expand fast enough to beat the speed of light, which is separating them from us. And so we consider them as, since they won't affect us, we can't affect them. We're just going to say that there are other universes. But he does clarify during the interview that they all sprang from the Big Bang, which is, I thought, according to general relativity at least, that was a little dot that concentrated the whole universe. But now these people are changing the definition. They're pulling the rug underneath your feet because you say, look, what are you talking about? Other universes? And they're saying, well, if we can't see them, if we can't interact with them and never will, then we call that a different universe. But see, what the problem is that universe shares our space, our same space. The matter is different, like from a galaxy. Andromeda has different matter than the Milky Way. We're separated by space, right? But Andromeda is part of our same universe because we all swim in the same space, so to speak, right? If we can't see a galaxy and we can't interact with it and it doesn't affect us, who cares? What's that got to do with it? This is a conceptual issue. It's still part of the same universe because it shares the same space. Otherwise, the word universe, which means matter and space, or so I thought, are we saying that they have their own space inside that universe? Is it a bubble that somehow is separated from our bubble? We have our own matter, our own space. They have their own matter, their own space. What's in between us? What are we going to call that medium? This is the problem. The problem is his definition, like he says it's operational, is worthless garbage. That's what it is. It's nonsense because he'll never be able to make sense of it. It's easy to destroy his argument. He can't have a universe without space. And if that universe shares the same space that we do, because I don't think there's a cut in our space and, a different space continues, then we have to identify whatever separates our matter in space from their matter in space, because that's what a universe means, matter and space. And this is where the problem is. They're trying to get another of those dualities. They're trying to get the word universe to mean galaxy and galaxy to mean universe, but that galaxy is so far away that doesn't affect us, so we'll call it a universe. And that changes the discussion because they don't have to answer now the key word, which is space, nothing. What separates us from that universe? And he says interaction. That's what separates, the fact that we don't interact and never will. See, and that's not a valid physical separation. Okay. And so continuing here, today is it's just going to be an introduction on this. I'll get as far as I can. So one of the critics who looked at his book and took the trouble to read his book, I didn't take the trouble to read it, and I don't recommend you do either because I'm sure Mr. Krauss has nothing to offer. If you read one mathematical physics, you read them all. But one guy did read his book and has a criticism. He starts out by saying that, that we have a problem with a mathematical aspect. The fact that you, because you do mathematics, pretend to understand the universe and where the universe came from. And he says, Krauss mentions that math is in a most casually unimportant manner, as though math is only a footnote in physics. In physics, math is the alpha and omega. And in a universe from nothing, math is very much the whole argument. Or should I say, the foundation on which the whole argument is based. Does math even say anything about our universe? Good question. I mean, if we're going to talk physics, if we're going to talk about whether the universe had a beginning, whether it will have an end, or, and whether time also had a beginning and matter, etc., do we need math? This is a conceptual issue. We don't need math to figure this one out. So if Krauss wants to take the idea that our universe could have arisen from nothing as a real possibility by only using physics, he must convince us how this math is not fiction and how ultimate reality actually can be explained by this math god. And I thought that was a very interesting point that this gentleman raised because the question is, do we need math to resolve this issue? Did we ever need math to say that God created the universe? I mean, whether you accept that version or not. I mean, the question is, do we need any math? And hopefully not. Or you say, look, God had a magic wand, he went abracadabra, and there's the universe. That's how you would explain something like that. And here's the same thing. You don't need any math. I don't need to know how much inflation there was in the first billionth of a second after the Big Bang. I don't need to know any of that. I need to know the mechanism. How did you create something from nothing? That's what I need to create to understand, right? That process. Okay, and so that was one place where he was questioned. Here's another person who questions him. He was interviewed by a lady. Her name is Abby Martin. And obviously she's not an expert. She's just curious, brought him on the show and said, look, I'm going to ask you some questions. And says, and asks him about, his book. And this is what Krauss has to say. He says, one of the greatest discoveries and surprises in the last generation, if not in the last century, is that the dominant energy of the universe resides in empty space. Again, we have empty space full of energy. Okay, so how empty can that be? And he says, in nothing. He emphasizes that. So he talks about empty space. He says it resides in empty space. He says in nothing. But then space, he never defines what nothing is. We don't have every time he says nothing, he means something. That's the issue. You take a bit of space, get rid of all the particles, all the radiation, everything, and we find that space weighs something. And we don't understand why. So how can he say that it's nothing when he's saying that he takes everything out of there and he still ends up with something that weighs something? It made us realize that you can get a universe from nothing without any supernatural shenanigans. I don't know how he's going to do that because he starts out with something, he's saying it weighs something. That basically, by quantum mechanics and the laws of physics, I like the fact that they say laws of physics, meaning they're going to shove it down your throat through authority, right? We understand in principle an entire universe with 100 billion galaxies, each containing 100 billion stars, can come from nothing. Cause its total energy could be zero, and therefore you don't need to literally violate any laws of physics to create a universe. Okay, so he's gonna say that even though we have empty space, we have nothing. Empty space, we removed all the matter, everything out of there. We still have something because that empty space, that vacuum, whatever you want to call, whatever word you want to assign to it, weighs something. And what is that something? It's energy. So we're going to start with something, and that something is energy. So now we got to get to the bottom of energy. What the hell is energy? What do you mean energy? I thought you said space was nothing. I thought you were going to show how something came from nothing. Now you tell me, well, it's not really nothing. That nothing that I was talking about really contains something. We call that something energy. And that's what weighs it, has mass or whatever. Okay. Okay. So we have a problem. First, he's not the first one to mention this. That's the first thing we need to show. So don't go rushing to buy his book because what he has in the book has already been said by tons of people. Here's one of the guys who said it. He died recently, Mr. Hawking. He says, at the Big Bang itself, the universe is thought to have had zero size. Okay, so we have zero size. That sounds like nothing. And he said there are gazillions of particles in the region of the universe that we can observe. Where did they all come from? The answer is that in quantum theory, particles can be created out of energy. Oh, we always have that word energy in there. In the form of particle-antiparticle pairs, which we just covered a minute ago. Space is made out of particles and antiparticles, okay? And they're going to call that energy, and two particles get together and they form this energy thingy. And they separate, and I guess that's when things start happening, right? Things start existing. But that just raises the question of where the energy came from. Good question. The answer is that the total energy of the universe is exactly zero. That's the answer they give you. The matter in the universe is made out of positive energy. Now, twice zero is also zero. Thus, the universe can double the amount of positive matter energy and also double the negative gravitational energy without violation of the conservation of energy. So he explained it all mathematically. We have this thingy, this undefined thingy called energy. And energy is made out of particle-antiparticle pairs. So now you know what energy at least is made out of. And particles, they're vibrations of fields. And so there's these fields vibrating there. That is the energy, I guess. Full circle, right? You can see what these guys are doing. These guys are saying, look, the famous vacuum, the famous nothing that I was going to talk about, it turns out to be something. What is that something? It's energy. And what is energy? Well, energy is a particle-antiparticle pair that get together. And you put them together and they become energy. When you separate them, they become particles. So that's how energy becomes particles. What is particle? Particle is mass, right? And what is mass? Well, they're eventually going to come to the right conclusion, which is what a particle is. The definition of a particle today is that it's a vibration of a field. And essentially that's what the Higgs is. It's a vibration of a field. That's what they give these Nobel Prizes out for, because this guy shows that, the Higgs boson, as I call him, is a vibration of a field. A bunch of particles just vibrating there, think of all these springs. They're just vibrating. The vibration itself, locally, that's a particle. And one is a positive particle for whatever reason. The other one's a negative particle. They get together and they form space. So now you have empty space, but empty space is this energy, because when these two particles get together, they become energy. So space turns out to be energy. That's what it is, whatever energy is, right? So you can see where all this is going. We don't have a word for nothing in mathematical physics. We don't have a word for vacuum or space or nothing, all three synonyms really. And what I'm going to show in next time around, what I'm going to be talking about, is that we've never, since day one, had nothing out there. It's always been something. Something on top of something on something on top of something. There's always been a background, and that background is always a something. It's always an ocean. You never have the fishies swimming in nothing. They're always swimming in the cosmic ocean, okay? And that's more than just a word. It's literal. There's an ocean there. and they can never get rid of that ocean. And that's what I'm going to be discussing in the next session. Okay, so now you know the subject matter. If you think it's too boring to talk about nothing, well, then you can miss the next session. But stay tuned. I think it's going to be quite exciting to see where how we got to where we are today. I'm going to go through that history, and I think you'll like it. Anyways, I'll see you next time, which is Sunday, same time, same station. Hopefully, I'll see you in Boris in June. And so until Sunday, we'll see you then. Bye bye.